Okay, so here's my, I guess we're on part D now. Here's my last example of a pigeonhole principle problem. We've actually done this as a project. And actually the Jackson and Thoreau had an example that reminded me of this, but this is not from this book, but it's similar to this one. So every positive integer has a multiple in base 10 consisting of just ones and zeros. So for example, 2, what's a multiple of 2 that just has ones and zeros in base 10?
10.
Okay. How about a multiple of 3? I'm going to let your brother answer this. What's a multiple of 3 that just has ones and zeros only in base 10?
111.
Yeah, 111. Good job. What's another easy one?
4.
4. Okay, great.
100.
100.
Yep.
All right. How about 1, since we've done 2, 3, and 4?
1.
1. Okay. Now, it's not obvious at all that this is a pigeonhole principle problem.
Yeah.
Because how many positive integers are there?
Infinite.
Right, so the positive integers can't be the pigeons.
Yep.
Because we can't have,
And there's infinite.
well, because there might not be finite in any number of holes, or who knows what's going on. Okay. But here's what we're going to do. This is a number theory / pigeonhole principle problem. This is a cool problem. We're going to start out with, it doesn't matter what our number is. Okay, we're just going to call the number we pick k. All right? And I'm going to start looking at the numbers 1, 1, 1. So 111, 111, 1111, etc.
Down.
Okay? All right?
Yeah.
And I'm going to look at, do I ever get a multiple of k here? Okay, so let's say, first of all, am I guaranteed to have a multiple of my number that just consists only of ones?
No, not necessarily.
Okay, why?
I mean, you could have multiples of 3,
Yeah?
but like even numbers.
Yeah, why can't an even number have just ones in
Because
it?
all of these are odd.
Yeah. It would sure be pretty odd to have an even number turn odd, right?
Yeah.
Okay. So I might not ever get a multiple. Even with an odd number, I might not get a multiple. For example, 5, I'll never get a multiple.
Yeah.
Okay? But I can look at the remainder. So here's the remainder is going to be 1 with 1. The remainder is going to be something. For 111, the remainder is going to be something, maybe something different, something prime. For
Who knows?
something prime prime. Okay, but what can I say about the remainders when I pick my number k?
Well, the remainders have to be from 0 to k minus 1.
Yeah, the remainders have to be from 0 to k minus 1, so I only have k possible remainders. If I ever get 0, I'm done.
Yeah.
I found a number. So there's only k choices. So once I do go up to k plus 1 ones, however big that is, but it's some finite number, right?
Yeah.
What am I guaranteed to have had happen here?
You're guaranteed to have had, well, not all these remainders.
Yeah, I might not have had all the remainders. In fact, we talked about that. You might have a box that doesn't have a pigeon in it.
Yeah.
But once I've done k plus 1 numbers, what can I say for sure about the remainders?
You're going to have gotten a remainder.
Well, I always get a remainder.
Yeah.
Two remainders are going to be used. One remainder is going to be used twice.
Yeah,
One.
I'm guaranteed to have found some remainder that's been used twice. So maybe it's 1, 1, 1, 1, 1, 1, 1. So 1,111,111 and 1,111 have the same remainder. Let's say it's remainder 4, remainder 4. Now once I know that, how can I find a number that just has ones and zeros that's divisible by k? In other words, the remainder is 0.
Subtract.
And the remainder should subtract.
So I would get 1,110,000 exactly, and that would be divisible by k.
Yeah.
I'm guaranteed after k plus 1 numbers, just looking at the ones, 1, 11, 111, I'm guaranteed to have found 2 numbers that have the same remainder.
Yep.
It turns out these numbers are really easy to subtract, the smaller one from the bigger one.
And subtract.
And subtract, and I have found some number Now, I will never know what it is. I just know it exists.
Yeah.
Right? But I will have found a number that starts with all ones and ends with some number of zeros.
And it's divisible by your number.
And is divisible by the number we started with.
Cool.
How cool is that?
Didn't know, like, it's kind of like binary.
Yeah, it is kind of like binary. I don't think this would work for all numbers. It was something was special about ones and zeros here. Like I couldn't do it with sort of like 3s and 5s. Why not?
Because
Well, there'd be some numbers, like all even numbers wouldn't work that way.
Yeah, all even numbers wouldn't work, but ones and zeros it did work.
Cool.
So that's another really neat pigeonhole principle problem. So the pigeonhole principle itself seems really simple.
But it couldn't be applied to like really complex stuff.
Yeah, and also really surprising stuff where it's not obvious at the beginning that this is a pigeonhole principle problem.
Yeah.
So that's pretty cool. So that was a great video, once again, from Kelsey Houston Edwards. I really like her videos.
Yeah.
All right, great job, guys.